Hey everyone, so in this video we'll conclude this, this mini section on all these tests for convergence and divergence of series. And what was the whole point, right? Some of you may be thinking that. And remember, again, what we've been doing so far is, okay, we've started by defining sequences. Right? So if a sub n gives you a formula for your sequence, then you have terms a sub 1, a sub 2, a sub 3, and so on. And the series is what you get when you try adding all of these terms. And in the past few sections, we've been wondering, what conditions should these an terms satisfy for you to get a finite value for this sum. And this is important because once we start representing functions as these series, right, that's sort of a spoiler for the next few sections, we will be concerned with a question of, well, does this series actually represent that function, like for these values of x in the domain? Or like the question, where is this representation valid for this function? But yeah, we'll talk about that in a later video. For now, I just want to summarize the tests that we've seen so far to help us determine convergence or divergence, and in some cases, absolute convergence or conditional convergence. Right? So essentially, one thing that you should always try when you're testing series is the test for divergence. Again, as the name suggests, it detects whether a series is divergent by looking at the limit of a sub n, right? If that a sub n term goes to something other than 0, then there's no way the series can converge. Otherwise, right, so you apply the test. If an does not go to 0, then you're done. It's divergent. Okay, now what if an does go to 0? So the test for divergence doesn't tell you anything, right? It might converge, it might diverge. Some other easy things you can try is maybe recognize what kind of series you have. Right, so maybe it's a geometric series. Or a p series, which is a series of the form 1 over n to the p. And for these types of series, it's easy to tell whether it converges or diverges, right? So for geometric, we know that it just depends on whatever your common ratio is. If it's strictly smaller than 1 in absolute value, it's convergent. Larger than or equal to 1, it's divergent. For p series, as long as p is larger than 1, it's convergent. Okay, so what else? So if your series does not fall into one of these categories, geometric or p series, well, then you try some other test for convergence. Right? So for instance, what other tests are there? There's alternating series. If your series is an alternating series, then you try the alternating series test. Right? And I'm not going to write down all the conditions here, right? But that's one thing you can try. If you have a rational function or an algebraic function, you can try a comparison test. Right? So I'll write them down here. If it's alternating, you try alternating series test. If it's rational, maybe algebraic with some powers of n in there, it's comparison. And there's also the integral test, which is not my favorite. It's quite limited. And here you need a function f that's positive, decreasing, and continuous before you can apply the integral test. Right, so but now it depends what type of series you have. And that will tell you what test you want to try applying. Of course, there are also the more general purpose tests, right? Your ratio test and your root test. And these actually tell you whether it's absolutely convergent or divergent. But keep in mind that the ratio test can only be applied if n is not rational, right? Or algebraic. Because otherwise it will be inconclusive. The root test, similar with the integral test, like I don't really like it that much. It's not really like widely applicable. But if you have, well, a term that's raised to the nth power, then that's clearly one thing you can try. So let's look at some examples of some series where we'll try to apply all of these tests that you see on this slide right now. This one, for instance, n times sine of 1 over n. It's So do you want to try this first? Like, give a minute or two to think about this, and pause the video right now. So, okay, did you pause the video? What kind of test did you try here? Did you try the test for divergence first? What happens if we do that? So what's going to happen there is you take the limit, as n goes to infinity, of your a sub n term. Okay, now what's this limit equal to? You'll notice that, well, n goes to infinity, sine of 1 over n. 1 over n goes to 0, so this is sine of 0, which goes to 0. So that's an indeterminate form, which tells me, let's try something like this. Rewriting it as a fraction with sine of 1 over n divided by 1 over n. And now this is actually something that goes to 0 over 0, on which you can apply L'Hopital's rule. But also you can just recall from your differential calculus classes the special limit sine x over x as x goes to 0. Remember, this is equal to 1. And that's exactly what's happening here. 1 over n goes to 0. And you have the same term here, right? In order to apply this limit, whatever's here and here must be the same thing, going to 0. So that's equal to 1. And just from here, I can conclude that n times sine of 1 over n is divergent. Now, one thing you could have tried here as well is, well, actually computing terms, right? 1 times sine of 1, 2 times sine of 1/2, 3 times sine of 1/3, so on. Right? Use a computer, see what you got. You'll see that it doesn't approach 0, it approaches 1. And that shows you that it can't be convergent. Let's look at another one. How about this one, where the numerator of your term is given by this pattern, right? This product, 1 times 3 times 5, and so on until 2n minus 1. In other words, all the odd numbers from 1 to 2n minus 1. And then your denominator is 5 raised to n times n factorial. So, okay, you can apply the test for divergence there if you want. But that's probably going to go to 0. Right? How do I know that? Well, n factorial down here. And then you have all of these terms up there. And there are n terms here as well. So you have n terms here, you have n terms here inside n factorial. But the n terms up here are roughly like double, term by term, than the ones in n factorial. But then you have that 5 to the n term here. That balances that out, which tells me that the denominator is going to be growing faster than the numerator. So this is probably going to go to 0 when I look at the limit. All right, so let's not actually evaluate the limit. Let's just apply one of our tests right away. In fact, it's a factorial, so don't do this, you don't do this, you just have to apply one of the tests. And in fact, if you have a factorial, the ratio test is going to be nice. So you can see here, an is equal to 1 times 3 times 5 all the way to 2n minus 1 divided by 5 to the n times n factorial. So what does the ratio test tell us to do? Limit as n goes to infinity of the ratio of an plus 1 over an. Okay, what's an plus 1? So it's 1 times 3 times 5, 2n minus 1, 2n plus 1, right? This is the term I get when I plug into, well, when I plug in n plus 1 into my last term here. And I divide that by 5 raised to n plus 1 times n plus 1 factorial. And then I divide by an, or that's the same thing as multiplying by the reciprocal. So I'm just going to multiply by this term over here. And look what happens. Since I have a factorial, well, n plus 1 factorial is simply just n plus 1 times n factorial, which means this cancels with that whole thing. Also, all these terms cancel with all these terms. 5 to the n plus 1, well, I can cancel out 5 to the n from that, leaving me with just 5 to the first power. So summarizing, on top I just have 2n plus 1. At the bottom I have 5 times n plus 1. And this tells me the limit is 2 over 5, which you can see if you just divide the top and the bottom by n. Right, so that's 2 over 5 times 1. Therefore, by the ratio test, this is absolutely convergent. Right? I mean, its terms are all positive, right? So if you say it's convergent, then it's absolutely convergent, because its absolute value is itself. Okay, so that was nice, right? The ratio test really helps when you have a factorial in there, because a lot of the terms cancel out. Okay, now look at this one. It has an n squared as an exponent. So maybe, just maybe, the root test is going to be useful here. Okay, well, let's try it. N over n plus 1. So it's technically absolute value an raised to 1 over n, right? But the terms here are all positive anyway, so I'm not going to write the absolute value. N squared raised to 1 over n. Aha, what do your laws of exponents tell you? This is n squared times 1 over n for your exponent, which means it's just n here. So you still have an n in the exponent. So what do you do here? Well, you first try to see what happens to these terms. As n goes to infinity, we know that n over n plus 1 goes to 1. So this is also an indeterminate form. right? It's 1 to the infinity. And how do you deal with a limit like this? It's not infinity over infinity or 0 over 0, right? It's 1 raised to infinity. So there are a number of ways you can approach this. In fact, if you rewrite the term inside, maybe you'll recognize a special limit in there. But if you remember in differential calculus, what you probably remember is setting y equal to that term and taking the logarithm of both sides so the n goes down. So now you're going to take the limit of ln of y first instead. Right? So the advantage of doing this is that by bringing that exponent down, this is now infinity times 0, and you can rearrange the terms here. And now you get 0 over 0, where you can apply L'Hopital's rule. So I'm not going to do this till the end. I'm going to leave this here for you to practice on. But whatever you get here for the limit, that's going to tell you that, well, if this is y, it's the same thing as e raised to ln y. But if ln of y approaches whatever this quantity is, then it's e raised to that quantity. And then you can use that to apply the root test, as long as that quantity is not 0. Right? So yeah, try doing that and see what you get.